Hi everyone, my name is Chiara De Luca. I'm a PhD student at La Sapienza University and in the INFN in Rome. Today I'm going to try to give you an overview on some works we have done within the work package 2. The aim of this work package is to investigate and understand brain states and their cognitive features. So in this work package, we work with the different kinds of data, lots of different lines of research, starting from experimental data to simulated ones and theoretical methods. And we try to integrate them to get a coherent understanding of brain states. So, okay. Here's a complex diagram of what we are doing and what we plan to do in the future. I'm not going into detail about this, but I'd like to just give you a general idea of what we are doing, what we plan to do. So on one side, we have experimental data, loads of experimental data acquired with different techniques. Each of them gives us an idea of different brain states analyzed with different aspects and in different scales. On the other, we have simulated data. Simulations might be done from data-inspired simulations, relying on theoretical methods, but they might also be data-constrained simulation whose parameters are inferred directly from experimental data. So in order to get a coherent understanding of what is happening, we need an analysis tool. So in the middle, we have this tool of analysis that should be able to get in input different kinds of experimental data, but also output from simulated data in order to compare them and evaluate them and validate the theoretical models underneath. So I'm proposing you a much easier version of that diagram. And this is what I'm gonna talk to you about today. In the middle, we have this analysis tool that should be versatile enough to get in input all these different kinds of data. We obviously have experimental data that comes in different ways and organized in different methods. And then we have data-inspired simulations on one hand, relying on theoretical frameworks, and data-constrained simulations whose parameters are get from experimental data themselves. So for what concerns data-inspired simulation, we first need a theoretical understanding and theoretical idea of what is happening. For what concerns for us, we are working toward building a theoretical framework studying the effect of deep sleep on internal representation of memories. So we propose an extremely simplified thalamocortical network, and we show that a deep sleep-like activity on it might perform a density-based clustering on the stored memories, meaning that during the sleeping phase, similar memories are grouped together, leading to some beneficial effects of this deep sleep-like activity. First of all, we can see there's a reduction in the energy consumptions for when the network is performing the same task before and after the sleeping phase. We have a reduction also in the information entropy carried by the network without losing any kind of information. So the network, thanks to a deep sleep-like activity, is optimizing its parameters, is optimizing its memories, capable to do the same things, but better and with less energy consumptions. So we built this simplified thalamocortical model, and on that, we implement data-inspired simulations. So simulations that aim at reproduce some features observed in experimental data. To do so, we implemented the thalamocortical spiking models using the NEST platform, and we show that this model is capable to express a deep sleep-like state that has comparable features with biological measurements. This model is also able to incrementally learn some MNIST examples. And we show that this deep sleep-like activity in this model leads to beneficial effects of sleep that are known to be observed in biological knowledge. So we show that sleep here performs homeostatic selective synaptic downscales. We show that during the sleeping phase, synaptic distribution is sharpened, and that the network during the sleeping phase is capable to create novel association. So we are also interested into the understanding of how the network working point changes within a brain state and when transiting from one brain state to another. So we made the first step towards that direction, and to do so, we evaluated the simulated network working point before the sleeping phase in an awake state, the blue area in this diagram. Then we want to study how it transited from this awake state to the beginning of the sleeping phase that is depicted by the red area in the diagram. Then we want to study how sleeping phase affects the network working point, moving from the red area to the orange one. And then back, we want to analyze the transition from the sleeping phase to the awake stage, evaluating the network working point after the sleeping phase in the green area. So in the future, we plan to expand this diagram, having a theoretical understanding of how this cycle is performed and how it affects the network activity and energy consumptions. Okay, so here's an idea of how data-inspired simulation works. We have a theoretical framework. We're relying on this framework to build the data-inspired simulation, and we compare the behavior of this simulation with experimental observables. Now, we need this analysis tool, and we've been working towards that together with the Jülich University mainly, and we aim at build a tool that should be capable to get and input different kinds of data from the different experimental techniques, but also different kinds of simulated data, and to get in output some observables that we want to be coherent and comparable with each other. Okay, so thanks to this tool, we can also do some data constraint simulations and not only data-inspired simulation. How do these work? So first of all, we need experimental data. And then we propose these data constraint simulations that are a data constraint models of the whole hemisphere of a mouse under anesthesia. The parameters of these simulations are inferred from the experimental data. So these will be extremely brain specific. This will extremely be dependent from the specific experimental data we are using for the inference. We are focused mainly on the spontaneous dynamics on the model. And here's a point I'd like to be clear on. We are not aiming at reproducing through the simulation a perfect copy of the experimental data over which we are making the inference. We aim at having a model who performs a spontaneous dynamics to be comparable with experimental data. We want these spontaneous dynamics to have the same feature from experimental data, not to be the exact copy of experimental data. That might be easier than what we are doing. Okay, so in order to do this, we need an analysis tool I just talked to you that should consistently compare and study experimental and simulated data. So we start from experimental data. We use the wide field imaging of cortical activity in ketamine anesthetized mice provided by LENS. In this data, we have access to a large portion of the brain with a nice spatial resolution. The signal is related to excitatory neurons and depends on the fluorescent indicators. This adds an optical timescale with a temporal artifact that we solved through the application of a temporal deconvolution in order to get a spiking-like signal you can see depicted in the pictures in blue. Okay, so we analyzed through the analysis tool I talked to you before 8 sets from these experimental data, and we decided to focus on the second and the third because they have comparable characteristics. We defined 3 main observables and we focused on them, specifically local wave speed, local slow oscillation frequency, and local wave direction. Okay, so then we have our experimental data analyzed, and we want to use that data to build a data constraint simulation. This, we do that through the application of a 2-step inference method. In the first step, we perform a likelihood maximization, and in the second, we make a direct comparison. So in the first step, we optimize 3 parameters, namely connectivity, adaptation, and external current, whereas in the second step, we adjust the parameters through an a posteriori comparison between the simulation output and the experimental data used for the inference method. Okay, so let's see what happens after the sleeping phase, that is in likelihood maximization. Here you can see the experimental data activity in the bottom and the simulated data activity in the top. They're not quite alike. In the bottom, there's quite a complexity in the activity, and we have some black regions depicting some long down states in the cortex, whereas in the top simulated activity, we can see that it is more stereotyped. Even looking at the observables we defined, so the wave direction and the slow oscillation frequency, we can see that the experimental data have quite a more variety in various characteristics, whereas the simulated ones are still stereotyped. So we need a second step, that is a comparison and adjustment made a posteriori. So we infer the parameters, we make the simulation, then we a posteriori move some of these parameters and compare the simulation outputs with the experimental data. We perform the Kullback-Leibler divergence in order to identify the optimal set of parameters leading to the best match between experimental and simulated data in all three observables we defined, that again are local velocity, local direction, and slow oscillation frequency. Here's the observables for the optimal match we could found for this data. And you can see a comparison on your left of the activities depicted. So in the top line, we have experimental data again. In the middle line, you can see the simulated data after the first step of inference, so only the likelihood maximization method. Again, they are quite stereotyped. And then we perform the second step in the inference method, and we get the simulated data depicted in the bottom. You can see these simulated data reproduce the main feature of experimental ones. They have quite a complexity and a variety in their expression. We get the same idea looking at the wave direction and slow oscillation frequencies observables. Again, in blue, you can see the experimental data, simulated data after the first step, really stereotyped in the middle. And then in the end, the simulated data after the second step, we call the outer loop, where we reproduce the complexity of the experimental data we inferred from. In order to make a more quantitative evaluation of this, we computed the entropy associated to all these observables, to this activity associated to the complexity of the dynamics reproduced. The experimental data are depicted here in the with a dot line, and we can see that after the second step, we get quite a close entropy, even a little bit higher. Whereas after only the first step, the inner loop in the simulated data, we can see the entropy, so the complexity of the dynamics reproduced quite lower. Okay, so here's really quickly what we are trying to do. We are trying to increment, to infer, to converge different lines of research. On one hand, we have experimental data, obviously, that needs to be analyzed and maybe compared. Then we have data-inspired simulations that rely on theoretical framework and whose output needs to be compared with some experimental feature. But we also have data constraint simulation who take experimental data as input in order to apply the inference method and infer the best parameters for these simulations, data constraint simulations. So what we plan to do in the future? First of all, we want to further develop the integration of these different lines of research. We'd like to implement some plastic cortical modules capable of incremental learning. We want to refine our theoretical formal understanding of the underlying mechanisms producing the beneficial effects of sleep. Till now, we have only been focusing on deep sleep, but we'd like to extend this analysis to different stages of sleep. And we also like to build some simulation of cortical slow waves on larger portions of the thalamocortical system. So develop the data constraint simulations from that. Okay, so I finished. Thank you very much for your attention. I will be happy to answer your questions. Thank you.